In this video, I'll be going over inverse functions and what it means for a function to be 1 to 1. So to start, let's look at these three relationships. First, let's determine if each of them is a function, and then if it is a function, let's discuss what it means to be 1 to 1. So remember, a function takes each input and points that input to exactly one output. So looking at the first relationship, it looks like each of the x values is pointing to a single, each of the x values, which are the inputs, is pointing to a single output. So we would say, yes, this one is a function. The second one, we have each of our inputs also pointing to a single output. So x1 goes to y1, x2 and x3 go to y2, x4 goes to y3, x5 goes to y4. So even though that both x2 and x3 are going to y2, that doesn't matter because each input is only going to one output. Now contrast that with what's happening in the third relationship where x2 is pointing to two separate outputs. So we would say not a function here. Alright, so for the two relationships that are functions, we notice something a little bit different between the first one and the second one. In the first one, each input goes to exactly one output, and each output is coming from just one input. So y1 is only getting pointed to by x1, and so on. Contrast that with what's happening in the second relationship, where y2 is getting pointed at by two separate inputs. So this distinction is referred to as a function being 1 to 1. So we would say this first one is 1 to 1. The second one is not 1 to 1. And we don't need to concern ourselves with the third relationship because that's not a function. So what is the definition of 1 to 1? We say that a function is 1 to 1 if each output corresponds to exactly one input. So this aligns with what we were saying. This first relationship, each output value over here, the y values, corresponding to one input value. And this is different in the second relationship where y2 is getting pointed at by two separate input values. Graphically, we can test for a function being 1 to 1 by using the horizontal line test, which says if a horizontal line can be drawn that touches the graph in more than one place, the function is not 1 to 1. So this first graph, if I draw a horizontal line right here, I touch the function in two places, so we'd say this is not 1 to 1. The second graph, no matter where I draw a horizontal line, it's only going to touch the function in one place, so we would say that this one is 1 to 1. And then the last one, we can draw a horizontal line right here. It touches in two places. We would say not 1 to 1. And so this relates to what we saw back here when we were in this middle relationship where one output is getting pointed at by two different inputs. So let's look at this third graph, and what we see is those two locations that I circled have the same y value, and that y value is positive 2. And so positive 2 is getting pointed at when x is negative 2 and when x is positive 2. So that output value, that y value of 2, is getting pointed at by two separate x values. So again, this is just a different way of seeing that a function is not 1 to 1. So let's move on to what it means for a function to have an inverse. If a function, f of x equal to y, is 1 to 1, so that's what we were just talking about, f inverse of x is an inverse function if x is equal to f of y. So this notation, f with negative 1 as the exponent, we say f inverse. Okay? So if a function is 1 to 1, we can find its inverse function. And what we notice here between these two equations is the x value and the y value are swapping places. And so what's happening is the input and the output of a function, so if this is the original function, the inverse function, each of these swap places. So the output becomes the input, and the input becomes the output. Okay, so in the next couple slides, we're going to see how we can actually find an inverse function and how to evaluate inverse functions. In this example, we have a table that shows the distances in miles that a car has traveled in t minutes. Find and interpret f of 50 and f inverse of 70. All right, let's look at f of 50 first. F of 50. What this means is at 50 as the input, what is the output going to be? Well, the input on the regular function is the number of minutes. So when a car has traveled 50 minutes, it has gone 40 miles. So this means after 50 minutes, the car has traveled 40 miles. All right, when we look at the inverse of 70, now it's saying going in the opposite direction. And again, when we have an inverse function, what's happening is the output becomes the input becomes the output. So here, this was the original output, and this was the original input. So we were inputting a number of minutes, we were getting out the number of miles. When we're talking about the inverse function, we're starting with the output, and we're going to see what that input is. So this is saying, f inverse of 70 is saying, after 70 miles, or if the car has gone 70 miles, how many minutes has that been? And that would be 90. So the car has traveled 70 miles after 90 minutes. So that's how we can interpret an inverse function from a table. And let's do something similar with a graph of a function. Sorry, it's a little blurry. But it says find g of 5 and g inverse of 1. So g of 5, that means 5 is the input value, or 5 is the x value. So we're going to start at 5, and on the y-axis, or the value of the function, we're getting 3. So g of 5 is equal to 3. Now for g inverse of 1, now we're going to take 1, but instead of starting on the x-axis, we're going to start on the y-axis. So y of 1, and that is hitting the function at 3. So each of these are equal to 3, which is just a coincidence. But hopefully you can see how we evaluate the regular function and the inverse function. Now let's evaluate, or rather, let's find inverse functions for given functions that we have the algebraic formula for. So find f inverse and g inverse for each of these two functions. So to find those inverse functions, we'll follow these steps. First, we want to test to make sure that the function is 1-to-1. Then we want to solve for x. We swap x and y, and then we write with function notation. So let's actually start with g of x first, just because that function is a little bit a little easier to see. So I'm going to graph this just to check for the function being 1-to-1. So the parent function here is the square root function. I'm going to go right 4 units, left 2 units. So we would end up at a graph looking like this. So right 4 up 2, same shape. So we would say that this is 1-to-1 because this passes the horizontal line test. So now that we know that this function is 1-to-1, we can proceed with the rest of these steps. All right, so I'm going to take this function, the g of x function, solve for x, but before I do that, I'm going to replace g of x with y here. So I'm going to write it as y equals 2 plus square root x minus 4. So I'm going to solve for x, subtract 2 from both sides, and then I'm going to square both sides to get rid of the radical. Y minus 2 squared is equal to x minus 4. Add 4 to both sides. And then, so we've solved for x. I'm going to swap the x and y. So we end up with this, but then I'm going to write with function notation. So instead of writing y, I'm going to write g inverse of x. So that is the inverse function. And let's look at the graph of the inverse function and the original g of x function and compare what these look like. So what we have here, let me erase this. What we have here is we have the original g of x function, which was this. This is the square root function. And what was it? 2 plus square root x minus 4. And then the inverse function, we have g inverse of x was equal to x minus 2 squared plus 4. Now at first glance it might not appear that these graphs are related in any way. But if I get a mirror image to make this graph symmetrical, what we might be able to see is that these graphs are reflected about this line y is equal to x, which is sometimes called the origin. And that will always happen when we have a function and its inverse. Those functions will always be reflected about that line y equals x. Now the reason the bottom half of this g of x function is not here is because if that bottom portion was there, this would not be a function. It would not pass the vertical line test. So what we're doing is we are restricting this to ensure that this is in fact a function by just having the positive portion of that square root function. All right, and then let's find the inverse of f of x. So I'm going to swap out f of x with y. And then I'm going to solve for x. So I'll multiply both sides by x minus 2. So y times x minus 2 is equal to 3 over, sorry, we got rid of the x minus 2. So distribute xy minus 2y is equal to 3. And then I'm going to divide by y. So x is equal to 3 plus 2y divided by y. So we've solved for x. I'm going to interchange x and y. So we get y is equal to 3 plus 2x over x. But instead of using the y, I'm going to write this with function notation. So f inverse of x as the inverse here. I'm going to let you verify that by graphing if you'd like. All right, so we verified that g of x and g inverse of x were inverses by looking at their graphs. We can also do this algebraically. And how we do that is we must show that g of g inverse of x is equal to g inverse of g of x. So in other words, we're using each function as the input of the other. And if those are equal, then these two functions are in fact inverses of each other. All right, so let's go for it. So on the left-hand side, I'm going to use the inverse function as the input of the original function. So the original function is 2 plus square root x minus 4. In place of x, I'm going to use this. So x minus 2 squared plus 4. And then I need a minus 4. So is that equal to, now I'm going to take the inverse function, and in place of x, I'm going to use the g of x function. So 2 plus square root x minus 4 minus 2, that is all getting squared, plus 4. So we'll just do some simplification here. On the left-hand side, I have 4 and negative 4, so that's going to be 0. 2 plus square root x minus 2 squared. On the right, 2 and negative 2 are going to cancel, so we get square root x minus 4 squared plus 4. On the left side, the square root of a square is just x minus 2. And 2 plus that, we just get x. On the right-hand side, when we square a radical, we just get the radicand, x minus 4 plus 4. We're left with just x. So those are the same. So because those are the same, we have done this verification. All right, let's look at an example. An object dropped from a height of 200 meters has a height, h of t, in meters after t seconds have lapsed, such that h of t is equal to 200 minus 4.9 t squared. Express t as a function of height, h, find the time to reach a height of 50 meters. This statement express t as a function of height. What that means is we want to find this function, t of h. So in other words, we want to find when we input a height, what time has elapsed. Another way of saying this is what is the inverse of the original h function. So these are going to be the same. So either way we want to think about this. So essentially we just want to find the inverse of that h of t function. So h of t is equal to 200 minus 4.9 t squared. Okay, so we're going to solve for t. So I'm just going to keep using the h of t notation. So subtract 200 from both sides. Okay, then we're going to divide by negative 4.9 on both sides. That's equal to t squared, and then we'll take the square root to get t by itself. So square root h of t minus 200 divided by negative 4.9. So h of t, that's just the height, and then t is this new function. So I'm going to rewrite this as t of h, so h is the input, and we're going to say h minus 200 divided by negative 4.9. So we have expressed t as a function of h, and now we want to find the time to reach a height of 50 meters. So if h is 50, we're going to evaluate t of 50. That's going to be equal to square root of 50 minus 200 divided by negative 4.9, and then take the square root of that. Simplifying the radical, we get 30.6122, and then taking the square root, we get about 5.533. 5.533. So what that's saying is when we input a height of 50, it takes 5.533 seconds. So the object, it has a height of 50 after 5.533 seconds. All right, lastly, let's talk about restricting the domain of a function. All right, in this graph, it's an absolute value function. We can say that this function, it's the absolute value function is shifted left 5 units and up 3 units. So we could write this as x plus 5 absolute value plus 3. All right, so right now that function has a domain of negative infinity to positive infinity. One problem with this function, though, is that it is not one-to-one. It's not one-to-one because it doesn't pass the horizontal line test. So a common thing that we will do with a function is restrict the domain so that the function is one-to-one. And so what we want to do is instead of having the domain be negative infinity to positive infinity, we want to make that domain smaller. And then once the domain is made smaller, that function will be one-to-one. So what we could do is we could eliminate everything to the left of negative 5. So if we were to do that, we could say if this domain is from negative 5 to infinity, and we can include negative 5, then everything on the right-hand side of this absolute value function will be one-to-one. It's going to pass the horizontal line test no matter where we are. We could also restrict the domain on the left-hand side. So we could also say that the domain is negative infinity to negative 5, and we can include negative 5. So that would also restrict the domain to allow this function to be one-to-one. So it doesn't matter which portion we restrict the domain to, but by doing that, that will allow the function to be one-to-one, and then we can find the inverse of that function.